Okay. Uh, I think I introduced you to the concept of random variable uh, last week, and of course, we are still on that. So we're gonna use the material for last week. Okay. So I'm actually gonna start from where we stopped last week. Okay, so like I said, you've been introduced to random variable, and I've walked you through what we mean by discrete random variable. We've done some example. Of course, I've explained the concept of probability mass function and example, and the discrete the CDF. We've done that as well, and I think um, where we stop, we actually stop on trying to find how to get a CDF of from a continuous random variable. And I could remember I gave you this an example. Okay, this is an example, or metal cylinder production. If you remember the other time, I said continuous random variable is measurement, is kind of the value of a random variable that you obtain by measuring. Okay, and of course, when you when you obtain the value of a random variable by measuring, of course, we actually going to have two bounds that I'm actually called the lower bound and the upper bound. Okay, and if you take a look at the example that I'm actually treating right now, of course, you actually going to see in this example, uh, the the lower bound is 49.5. That is the lowest, okay, and the highest is 50.5. Okay, and don't forget that I told you that if a random variable can take any value in an interval, okay, that's a continuous random variable. Okay, so and a continuous random variable is a variable that we when you obtain the value of a variable by measuring. Okay, just like what we're trying to do right here, we're trying to measure the diameter. Okay, we're trying to measure the diameter of a randomly choosing cylinder, okay, manufactured by a company. Okay, you got a company, what they do, they actually manufacturing cylinder. Okay, and you know what, every cylinder has a diameter, okay, that we can actually measure. Okay, and going by the history of this company, of course, the highest diameter, okay, of any cylinder in this company is, the lowest value you can, measurement you can have is 49.5, and the highest value you can have is 50.5. And don't forget that because we are in a stochastic world, okay, when you take a measurement, okay, you are not going to get the same value at different time. Okay, but you know what, they know the possibility, okay, of the kind of value they're going to get. Okay, and that's why we got a range like this. Okay, so the other time, of course, I explain to you what do we mean by probability density function. Of course, the probability density function is the name given to the probability distribution of a continuous random variable. Okay, last week I actually told you that the probability distribution is give us opportunity to know the possible outcome, okay, the possible events in the sample space, okay, with their corresponding probability. Okay, so which means that some outcome in the sample space has a greater chance of occurring than other. Okay, so what the probability density function is actually going to give us, of course, is going to give us how often, okay, you can have a particular value within the range, okay, how often they occur. Okay, and that is the reason why we're focusing on probability density function. Okay, like I said, the probability density function is a name given to probability distribution of a continuous random variable, why the probability mass function is the name that we give to the probability distribution for a discrete random variable. And of course, what I'm actually showcasing uh, right here, what I'm showcasing uh, right here is just to be able to tell you, um, you know, to be able to show you the way, the probability density function is actually going to look like. And of course, uh, looking at the probability density function f of x, okay, is it's a probability density function because it said it is equal to 0 or greater than 0. And you know what? The total area under a curve, okay, has to be equal to 1. That is going to be the total area under a curve for a probability density function. So it means if I have a probability modeling, if I have a probability model, and where the range of the continuous random variable is specified, what do I mean by that? Okay, you got a lower bound, you got the upper bound, and I integrate the f of s, okay, within the state space that I talk about. Okay, within that state space, it must give me 1. And you know what? The moment it gives 1, what that means is that it's a valid probability density. I'm actually going to write that because it is not all probability functions that are valid. Okay, PDF. Okay, so I'm trying to talk about, so this indicates, so this indicates, so this indicates that you know, f of x, okay, is valid. Okay, you know, it indicates that f of s is actually valid because it integrates to 1, because the total area under a curve equal to 1. Okay, and that is exactly what we need, because we may not be able to find the average, we may not be able to find the variance if the probability density function is a total area under a curve is not equal to 1. So it is required, okay, before you can go ahead to figure out the mean, whatever statistical essentials, okay, from the PDF. Of course, it has to be a valid PDF if it integrates to 1. Okay, I'm actually going to erase what I wrote right now. Okay, so the next thing I actually want to talk about is, if you are given a question, suppose that the diameter of a metal cylinder has a PDF. The PDF is actually going to be written as a lower case f. Look at that. Anytime you see a lowercase f, f of s, so this is actually indicating a PDF. Okay, that is indicating a PDF. Okay, I want you to take note of that. So, okay, that is actually uh, indicating PDF. And what I mean by PDF, of course, I mean probability density function. Okay, it must always be a lower case. Okay, the lower case. Now, some of you have seen your question. You ask the reason why how do they obtain the model? How do they obtain this? Okay, how do they obtain this? Of course, an engineer or a scientist or a modeler have studied situations in the company. Okay, don't forget, this company actually make metal cylinder. Okay, and they look at the behavioral pattern. Where they know the possible values of diameter that can be measured from the metal cylinder, which actually ranges from 49.5 to 50.5. Okay, so when you take values in this range, okay, if you plug in the values, okay, into this model, of course, it's actually going to give you different values of different probability value. Okay, so, and of course, that is what we actually plotted here. Okay, in the x-axis, of course, we actually have values in this range. Okay, and of course, if I decide to put the value into this function right here, I'm actually going to get the the respective probability function. Okay, so this is model. This is a model. Okay, this is more or less like a model. Okay, they've looked at the situation, and if you take a look at what I have here, if you expand what you have in the parentheses, of course you're going to have quadratic. Okay, and so I know you've heard about quadratic kind of form of equation or expression before. Okay, and that is why take a look at that. This is a, you can say the concave. Okay, this is more, this is a concave up. You can see that now. Okay, I think you can see that now. So that is actually you, of course you've heard about concave up and concave down. Okay, in the case of quadratic equation. So the engineer has looked at the situation, for them to be able to arrive at a model. Of course, what I this is a model right here. Give me 1 second. I'm actually gonna, I'm actually gonna write something right now. Okay, take a look at this guy here. It's a probability density function, and it's also a model. Okay, that's a probability model. Okay, and don't forget, I said something the other time. What do I mean by model? Model is a mathematical representation of reality. Okay, don't forget, don't, I told you the other time, we actually want to understand the environment we find ourselves, and because of that, we are modeling reality. Okay, part of the reality of life is that the diameter of a cylinder exists. And if the diameter of a cylinder is actually going to exist, of course, it must exist between 49.5 and 50.5, based on the provision and experience of this particular company. I think you get it now. So, uh, looking at it mathematically, okay, viewing situation mathematically, okay, about the curve, about the shape that come out of the situation. Then, of course, this is the mathematical modeling, and you know what? This is more or less this is a probability model. It's a probability model because when I plug in the value of a diameter into this equation, into this expression, I'm actually going to compute different probability value. Okay, the f of s right here represent the probability density function. Okay, and of course, this is going to be valid when it integrates, to 1. And what I'm trying to say right here, f of s is going to be equal to 0 when I don't talk about the range in this interval. So which means the probability distribution does not really exist when that really occur. Okay, so I'm going to erase that right now, and I'm actually going to continue to the next slide. Okay, so what I'm trying to do right here, when you are given a probability model, of course, you need to be able to test the validity of that probability density function. Like I said, it is not all probability function that is valid. That's a valid PDF. And how am I going to tell? Of course, I can only tell if and only if I integrate the probability function given over the state space, over the range. Okay? And of course, that's exactly what I'm trying to do right here. And of course, you can see that this actually gave me 1. Okay? And the fact, so because it gave me 1, then it shows that this probability model or this probability function is a valid probability density function. Like I said, it is not all probability function that are valid probability density function. Of course, they need to be valid because that will enable us to find the mean, the average, because we may want to find the average of a diameter, okay, of a metal, in this company. Okay, how do we tell about average? How do we tell about the variance? How do we tell about standard deviation? How do we tell about other statistical essentials? So to be able to tell, to be able to figure out other statistical essentials, then the probability model, the probability function we're using has to be investigated for validity. Okay, and of course, when it integrates to one over the range specified, over the state space specified, of course, when it integrates to one, then it's a probability, is a valid probability density function. Okay, so at times we may not want to consider the entire range. The focus may be on probably, you know, this particular region, okay, range. Of course, you also need to integrate that, but only that you're actually going to use a range specified, and of course, you're going to get a value lower than one. Okay, in this situation, you are only finding probability of the diameter of a metal cylinder lying between 49.8 and 50.1. Of course, this does not go over the entire range initially specified. Okay, and that is the reason why you actually get a result that is less than one. Okay, so the next thing I'm actually want to talk about is the cumulative distribution function. Now, by the way, what is the cumulative distribution function? You know, the cumulative distribution function is just trying to tell us what is the probability of a random variable less or equal to a particular value. Okay, what is the probability that a random variable less or equal to a particular value? And that is what I'm trying to say. The CDF is different from PDF. Okay, the CDF is different from PDF. The CDF, of course, symbolically, we use an uppercase F to denote that. Okay, so when you see this, that's a CDF, a cumulative distribution function. Okay, so the a cumulative distribution function is just the probability of x of a random variable less or equal to a particular value. But when you want to talk about the probability density function, the probability density function is actually looking beyond that. Okay, the probability density function does not cumulate. Okay, it's actually looking, at the probability of a particular, variable lies. A particular value lies in a given interval. Okay, different from the probability of if a random variable less or equal to a particular value. Okay, and if you want to find the CDF, of course you need to use the lowest range specified, the lower bound specified in the study. Okay, I'm actually using minus infinity right here because of course the lower bound in this word, the lower value in this word is minus infinity. Okay, I'm just trying to use that right here. But in the case of a particular study you are actually investigating, what you need to specify right here has to be the lower range. Okay, it has to be the lower bound. Okay, and that will terminate at x. So which means if you are given a function of x, you have to change that to a function of y. Okay, it's not necessary that you change that to a function of y. You could change it to a function of m. You could change it to a function of t. You could change it to a function of z. It doesn't really matter. But the only that since the upper bound of the range in CDF is x, of course you got to specify a function that is have a variable other than x. So right here I'm actually using f of y, and when I have f of y, and I'm actually going to integrate with respect to y. Okay, now so which means the CDF is when you get a CDF when you integrate the PDF. I'm going to say that again. You're going to get a CDF when you integrate a PDF, because this is a PDF right here. Don't forget that I said a PDF is a lowercase f, while the CDF is an uppercase f. And of course, now take a look at what you have done before in calculus. Okay, what you've done before in calculus. Okay, when you try to you know integrate PDF, that will give you CDF. Then it means when I differentiate CDF, that should take me back to PDF. That is exactly what I'm trying to do right here. This is like differentiating CDF will take me back to PDF. Integrating PDF, then I'm going to get CDF. I'm just trying to show you this just for you to know the connection between the PDF and the CDF. Of course, you know, integration means antiderivative. Okay, integration means antiderivative. Okay, now if I want to calculate the probability, if I want to compute the probability of a x, of a random variable x lies in an interval, what am I going to do? Okay, now when you take a look at this guy here, I actually want to find the probability of x lie between a and b. What am I going to do? What is the lower bound? What is the upper bound? The lower bound is a, the upper bound is b. If I want to do that, I'm actually going to start from the upper bound. Take a look at this guy here. The probability of x less or equal to b, because I'm talking about this guy. So, and you know what? The probability of x less or equal to b, that's going to be a CDF. Okay? That's why I have it. That's going to be a CDF at a point b. Okay? And then the probability of x less or equal to a, that's going to be a CDF at a point a. Okay? So, like I said, it's going to be CDF, okay, at point B, okay, and this guy here is going to be CDF at point A, okay. You can see that now. And here, this is a CDF. This is a CDF at point X. You can see that now. That's a PDF at a point X. So it means when you are given a question, you need to first find a PDF at a point X. Okay, when you find the PDF at a point X, then if you want to find the probability of X lie between A and B, okay, then you just need to plug in from the expression you got, you're going to plug in B to represent X, because your CDF we're always going to be in terms of X, because when you integrate this you transfer to Y and you plug in the range, of course, it's going to be in terms of X. So you need to plug in B into where you find X, then that's going to give you f of b, and you plug in a into where you have x, that's going to give you f of a, then you're actually going to subtract them. Okay, when you subtract them, then you have computed the probability of x lying between a and b. Okay, so that is how to figure that out. Okay, okay, so if that is taken right now, the next thing I'm actually going to do, okay, so the next thing I'm going to do right now is, given the function you were given initially, okay, don't forget you were given f of x equal to 1.5. I'm actually going to write that. You're given this, you're given f of x equal 1.5, okay, minus 6 into y minus 50.0, okay, squared. This is what we give. Excuse me. Give me 1 second. Okay. You were given that one. Can you see that now? This is a PDF. Okay. And when you were given that one, don't forget that the range of x, the domain, okay, the domain under which that function is defined was given as 49.5. Okay, was given as 49.5, and probably let me check the range, then 50.0. You can see that here. Okay, 49.5 to 50.0. Okay, now you're gonna see now. Okay, so 50.0 or 50.5. Let me see. That should be 50.5. Okay, 50.5. Okay, so when you take a look at that, this is what we're given. Okay, and they ask you to find the CDF. If you want to find the CDF, okay, you actually need to use the lower part to x. Look at that. The lower part of the range specified to x. Look at that. Then I'm going to change, anywhere I see x here, I'm going to change it to something else. Don't forget, I'm integrating from 49.5 to x. That's why I'm changing to y. Can you see that now? Integrating this right now, okay, this is what I'm going to get. Then I'm going to plug in x first. That's what I got. Okay, plug in S, then plug in the 49.5, that's what I got. And this guy right now, okay, this guy right now is actually f of x, the CDF at a point x. Okay, you can see that now. That's going to be CDF at a point x. Okay, that's a CDF. You know, the CDF at a point x will be in terms of x. You see that now? The CDF at a point x will be in terms of x. Can you see that now? Okay, so do you know that from here, I can actually compute this? And I'm going to show you right now. Now, if you are asked to find the probability of x lie between 49.7 and 50, I can actually make use of this. Okay, now if I want to make use of this, I need to first interpret this. Do you remember the other time I said when you were looking for the probability of x lie between A and B, that's actually going to be big F of B minus big F of A. You know that? Okay, so what I'm actually going to do right now, I'm going to interpret this as, you know, CDF at 50 and minus CDF at 49.7. Can you see that now? Then what I'm going to do, I'm going to plug in 50, because don't forget, this is my f of x. Okay, now if I want to get f of 50, I'm actually going to plug in 50 into anywhere I find s. Okay, that's what I do here. Can you see that now? Then I'm going to plug in 49.7 into anywhere I find s. That's what I do right here. Then when I, you know, I'll simplify that, and I subtract that, of course, I'm actually going to get 0.396. So which means if you want to find the probability that a particular random variable lies in a given interval, okay, so what you need to do, you need to first obtain your CDF at point S. And after obtaining your CDF, then what you just need to do is just to plug in the, you know, the upper bound into where you have x, then you plug in the lower bound into where you have x, then you're actually going to subtract that. Okay, don't forget, you're actually going to subtract the lower bound from the upper bound, and you're going to get your results. Take a look at that. That is a 0.396. So what is interpretation here? The probability that the random variable will lie between 49.7 and 50.0. That probability is 0.396. Of course, we're talking about cylinder, okay? We're talking about diameter of a metal cylinder, okay, in this particular company. So what we're trying to talk about, the probability that the value of a diameter, okay, of a metal cylinder will lie between, you know, 49.7 and 50.0 will be 0.396. So 0.396 is just going to tell you the probability that that is going to happen is 0.396, which is about 39.6%. Okay, 39.6%. Of course, they're actually going to have, you know, the value of the diameter of a metal cylinder, okay, is actually going to lie between 49.7 and 50.0. Okay, that's exactly what that is explaining. Don't forget, if you want to find the probability of you know, a random variable lies, you know, in a given interval, you need to first find your CDF. Okay, the moment you have your CDS in place, of course, the next thing you actually, I mean, CDF in place, the next thing you're going to do is to plug in the values of the upper bound and the lower bound specified in the question. Okay, so if that is clear right now, I'm actually going to, erase what I wrote, and I'm going to go into the next slide. Okay, so in the next slide, I actually want to explain this graph to you right now, because I actually got this graph from the CDF. Now take a look at this shape right here. That is the way the cumulative density is actually going to be. Okay, now this is more or less looking like the beginning of epidemic. If if you look at the the COVID, the Ebola, and the infectious disease, when they start, of course they're going to start like this. They're going to be going exponentially, okay, until they get to the maximum point reach, before it starts descending. Okay, but you know what, the CDF is not going to descend, but it's actually going to converge at 1. because the highest value you can obtain for the CDF is actually going to be 1. Okay, that's why it converges right here. Now, I want you to see what we've computed before. If you take a look at this guy here, with the probability of x less or equal to 49.7, okay, x less or equal to 49.7, what you are actually saying, you're going to start from the lower bound to this point, to 49.7, when you integrate. And of course, that is exactly what we have right here for 49.7. Of course, that is that is what we have here. Look at that. It means if I want to integrate it from the beginning, I'm actually going to do from the lower part. Okay, I'm actually going to start from the lower part, to 49.7. So my lower part still remain 49.5. The upper part this time around, the upper part is actually going to be 49.7. Okay, so from the lower part to the upper part, that is specified as 49.7, of course, that is actually going to give you 0.104. Okay, and that's exactly what I'm specifying right here. Okay, you can see that now from 49.5, start from here to 49.7. Of course, the probability is actually 0.104. And of course, if you take a look at this, the probability of x less or equal to 50 means I'm actually going to start from the lower part, then I'm going to stop at 50. And that probability is actually 0.5. And that's exactly what you have right here. Okay, that's what we have right here. Okay, so when what you just need to do to this equation, you're just going to plug in 50. And when you do that, this part will give you 0.5. So which is the probability of x less or equal to 50. Okay, and that is actually going to be 0.5, and that is what you have here. And don't forget, we're looking at the probability that x lie between 49.7 and 50. So which is this side? Can you see that side now? That side now, is what we computed to be 0.396. And how do I get the 0.396? Of course, you subtracted the 0.104 plus from 0.5. And that was why you got that. Okay, so this graph right here is showing, what we just computed. Okay, the next agenda of the day is actually to investigate, to talk about when variables are, when we have two variables that are, jointly distributed. Okay, we'll be talking about just single variable. Okay, but right now we want to talk about two variables. Okay, because we could have situation where two different variables are jointly distributed. Let me tell you this. What we just finished is more or less is called univariate. Okay, because we are only focusing on one variable at a time. But we could have situation whereby the focus is going to be on two variables. Okay, maybe in that engineering company, the the company is not only interested in measuring measuring the diameter of a cylinder. Maybe they also want to measure something else, okay, other than diameter. Okay, so, and I'm actually going to refer to that as x and y. Okay, so in a situation where x is discrete and y is discrete, okay, of course they can be jointly related. Okay, they can be jointly related, and they are jointly related. Of course, I'm going to have the probability of x equal to a particular value and the probability of y equal to a particular value. Of course, that probability will be denoted as Pij. Okay, so it means it's talking about the joint probability. You can only talk about joint probability if two variables are jointly distributed. I'm actually going to say that again. You can only talk about, okay, uh you know bivariate, okay, in a situation whereby two variables are jointly distributed. They are jointly distributed, and you know what, they for the two of them have to be discrete. X has to be discrete, y has to be discrete, or x has to be continuous, y has to be continuous. We shouldn't have the combination of that. Okay, that is not going to make sense. So the one we actually want to consider, we want to consider two variables that are jointly distributed, and you know what, they got the same nature. Okay, discrete discrete, okay, continuous, continuous. And of course, if they are discrete, of course, we're going to talk about what is the sum. You remember the other time when I was talking about uh, univariate, of course, I said the sum of that, must be equal to 1. Look at that. The sum of pi must equal to 1. Okay, that is when I have a single variable. Okay, that is univariately distributed. Okay, but in a situation where I got two variables that are distributed, okay, uh, that are discretely distributed, okay, of course, I'm actually going to have two summation because I got two variables. Okay, if I have three variables, I'm actually going to have, the number of summation I'm going to have will be 3. So the number of summation I'm actually going to have actually depends on the number of variables that I'm talking about. Okay, we got two variables right here. Of course, the double sum of the joint probability must equal to 1. That's according to the rule. Okay, and in a situation where I'm talking about continuous, okay, where s, a variable s, can be measured, can be obtained in an interval. The variable y also in an interval. Of course, we're talking about two variables that are jointly distributed, and you know what, two of them are continuous. Okay, if two of them are continuous, of course, I'm actually going to have double integral. I'm actually going to have double integral. Okay, when I have a double integral, I'm actually going to have the range for x and the range for y. Then the probability that I'm actually going to be talking about is going to be a joint probability. It's going to be f of x y. Okay, it's going to be joint probability, and that's what I'm going to have here, and that's what I'm going to integrate. Oh my God, this should be a mistake. I think what I want to write here should be the y. I'm actually going to change that. Okay, so what I'm trying to talk about is integral, f of xy, okay, the x, the y, okay, must equal to 1. And you know what? If the range of x is specified, let's assume that maybe the range of x is a b. I'm just assuming. Okay, if the range of y, is cd, then right here, i'm actually going to write the range, the ab here, and I'm going to write cd here. Okay, specifying the range. Okay, we're actually going to specify the range. The first integral is actually going to be the range of x. Okay, because I'm actually going to start the integral process. I'm actually going to start the antiderivative process, integrating with respect to x. And when I'm integrating with respect to x, I'm actually going to use the range of x. And whatever I got, I'm actually going to integrate that with respect to y, and I use the range of y, which is c and d in this situation, and that must integrate to 1. Okay, so the same way that we determine whether a probability function is valid when I'm talking about univariate, when I have a single variable that I said, when I integrate the f of x, it has, with respect to x, must equal to 1. So which implies the total area under a curve must actually be 1. Then the same way we're going to investigate variables that are jointly distributed, and these two variables are continuous in nature. Okay, so which means I'm actually going to integrate the joint distribution of x and y with respect to x, with using the range of x, and whatever I got, I'm actually going to integrate that with respect to y using the range of y, and the result must give me 1 before I can actually conclude that the bivariate, okay, that the bivariate density is actually a valid PDF. When I say bivariate, okay, so this is what I mean by bivariate. Bivariate. Can you see that now? When I say bivariate, it means I got two variables, okay? So that's what I got bivariate, okay? So that is how to go about this. Okay, so the next thing that I actually want to talk about right now is to talk about the cumulative function. When we were dealing with the univariate, I walk you through, uh, getting the cumulative function, for, for discrete random variable and for continuous random variable. Okay, of course, we're actually going to do the same thing when we're talking about, when in a bivariate situation. Okay, we are two variables jointly, distributed. Okay, when you take a look at what I have right here, I'm actually going to have an uppercase. Don't forget, an uppercase F. Okay, an uppercase F into XY. If you take a look at this one is a lowercase f. This is the PDF. Okay, right? This is actually going to be the CDF. Okay, the CDF is going to be an uppercase F. Okay, and don't forget, when we're dealing with the CDF of a univariate situation where you got a single variable, we said is equal to the probability of x less or equal to x. Okay, you remember that I said if you're looking for this, is actually the probability of x less or equal to small x. Give me 1 second. I'm gonna write that, for you to see clearly. Okay, so what I'm trying to talk about is that remember that for a CDF of a x, I said it's the probability of x less or equal to that. You remember that? But right now, I'm not only talking about a single variable, I'm talking about two variables, x and y. Of course, if I add x and y, then I'm actually going to write this probability of a biggest less or equal to a particular value and a y less or equal to a particular value, because I'm talking about bivariate. Okay, I'm talking about two variables. Okay, now looking at that in a discrete case, in a discrete case, of course, we're going to be talking about double sum of Pij. Okay, and when you're talking about double sum, of course, I got to make sure that x less or equal to x and y less or y less or equal to y. Okay, and if I want to get that from a continuous perspective, like if the two variables are continuous random variable and I want to get the CDF for that, then I'm actually going to have two integral. But we don't forget, when I have two integral, I'm going to start from the lower part of the range. Okay, I'm going to start from the lower part, okay, to that particular point. I'm also going to start from the lower part here to that particular, point. Okay, and don't forget, if you're given f of xy, if you're given f of xy, okay, you're actually going to change that to something else. Don't forget, you remember the other time when you are given f of x, if you want to find a CDF of x, which is an uppercase f of x, then you need to be able to change the f of x to f of y. You remember that? You're also going to do the same here. Okay, you started with s and y. Okay, you started with s and y. You're actually going to change s and y to something else. Okay, here I'm changing s and y to w and z. Okay, to w and z in whatever function given, and I'm actually going to be integrating that with respect to z, with respect to w, where the range of z, of course, the range of z is actually going to be from the lower part of that to y, and the range of w from the lower part of that to that. Okay, so of course, I'm actually going to walk you through how you can execute that. Okay, so I'm going to clean my board right now, and I'm actually going to walk you through. I'm going to go to the next slide. Okay, so the next slide now, I actually want to, apply, to identify situations whereby we could have two variables that are jointly distributed. And this example right here is actually going to be an example, for situation whereby I got two variables, two of them are discrete. And let's take a look at that. Okay, air conditioner maintenance. Of course, you know about air conditioner maintenance. Okay, so a company that services air conditioner units in residences, okay, and office block is interested in how to schedule its technicians in most efficient manner, okay? Because they know the capability, they know the ability of those technicians, okay? And they're looking for a way, you know, to be able to, you know, assign them, to residences in such a way that they they actually going to have, it will result to what I call efficient efficient allocation at the end of the day. Okay, so the random variable x taking the values 1, 2, 3, and 4 is the service time in hours. Now, the service time in hour is discrete because this is by counting 1, 2, 3. Don't forget. So it means the range of X here is 1, 2, from 1 to 4. That is the service time. Okay. Now, which means the lowest service time is going to be 1 hour. Okay. And the highest service time is actually going to be 4 hours. Now, there's another random variable y taking values 1, 2, and 3. And the 1, 2, and 3 is a number of air conditioner units. Okay. Now, in this situation, we got two variables. Okay. One is the other one, the service time is discrete, and the number of conditioner unit is also discrete. Okay. Now, what you are seeing right here, what you're actually seeing right here, of course, since we got two variables, we're going to have a cross tabulation, okay, where the values that you have here give the probability, okay, that gives the probability of the service of a particular service time and a particular number of units. For instance, the 0.12 right here is a probability that, the number of units one actually use a service time of 1 hour. Of course, this guy here is 0.21. Here is the probability that, the number of units or two actually use a service time of 3 hours. Okay, now take a look at that. The company has the record of this based on the past experience. Okay, they understand their staff, they understand the way they service, and that is the reason why some companies, they know those employees that they're actually going to send to a difficult places, because they know those employees, they have the capability to be able to, address issues. Okay, and that is the reason why when you find yourself working in a company, of course the company have a way to monitor your performance. Okay, so what I have right here actually give the probability of, like if you take a look at the 0.07 right now, it means the probability that the unit 3 will use service time for 4 hours. Okay, that is 0.07. Okay, so which means unit 3 is not necessarily to use up to 4 hours, because the probability is very, very small, which is 7 out of 100. Okay, which is a 0.07. Now that you understand what I put right here, because an examiner can give you something like this and ask you to figure out different kind of probability, question, can be given different kind of probability question. Okay, and that's why I actually want to take you this right now. Now, if I had from 0.12 to 0.07, if I had everything here together, it must give 1. Okay, it has to give 1. And of course, you know the reason why I have to put double summation. Okay, I put double summation because, of course, we got two variables, the service time and the number of units. Okay, so adding from 0.12 to 0.07, of course, we give 1. And giving 1 means you are verified that this is a valid probability mass function. Don't forget, when you are talking about discrete random variable, we're going to be talking about probability mass function. Okay, so this is valid because everything added up to 1. Now, the next thing that we actually want to do, if you take a look at this guy here, we actually want to find the cumulative. Okay, and what does that actually implies? I'm going to show you right now. What this implies is that what is the probability of x less or equal to 2 and y less or equal to 2. that is the same thing. Anytime you see a bigger an uppercase F, written that way. So what we are trying to do, what is the probability of X less or equal to 2 and Y less or equal to 2? And how are we going to figure that out? Okay, if you want to figure that out, of course, you're actually going to focus on this. That is 2, 2. Look at that. You're going to focus on adding that. That's exactly what you're going to do. You're going to focus on adding that, okay? So, and that's why you have a 0.12 plus a 0.08, and this guy here should be 0, it should be 0.08, okay? So this guy here should be 0. Let me write that here. It should be 0.08, okay? As you can see from here, I'm actually adding 0.12 to 0.08 to 0.08 to 0.15, of course. So that this place should be 0. So at the end of the day, that probability is a 0.43. Okay, the probability is a 0.43. If the service, what we're trying to say in essence is that, the number of service hour is going to be less or equal to 2, and the number of units is going to be less or equal to 2, then the probability is actually going to be 0.43. Okay, of course, I can ask you to find, any other, I can ask you to find F of 2 comma 3. Okay, and F of 2 comma 3 is actually, trying to find what is the probability of X less or equal to 2 and Y less or equal to 3. Okay, of course, you can actually figure that out. Okay, and that's going to be 2 by 3. Okay, so I can ask you to, to obtain stuff like that. Okay, so so far so good. I'm actually going to go into the next slide right now. Okay, so going into the next slide right now, the next thing that I want to talk about is what we call marginal probability distribution. You remember in probability, I walk you through what we call marginal probability last week, okay? And what do we mean by marginal probability? In a situation where I got two variables and I actually want to focus on one out of the two, that's marginal, okay? We can also figure out the marginal probability distribution, when we're working on distribution, okay? And of course, what we're actually going to do is by summing or integrating the joint probability distribution over the values of other random variable, the variable we're not interested in, okay? Now, for the discrete, don't forget I have S and Y. Like the case I'm treating right now, you have a service time and you have the number of units. But in a situation where I say, okay, you know what, I'm only interested in service time. If I'm interested in service time, then it means I'm actually going to sum, the joint probability with the respect to the level of Y. If I'm interested in the level of X, okay, I'm actually going to sum the probability of the joint with the respect, over the levels of Y. You see right here, because don't forget S equal to I, Y equal to J. Okay, now, and if I'm also looking for the probability of Y, okay, like I said, if I'm looking for the probability of Y equal to J, of course that is actually going to be summation Pij. Then I'm actually going to be summing over X. Okay, it means I'm marginalizing X. If I'm looking for Y, the probability of Y, I'm actually going to sacrifice X. If I'm looking for probability of X, I'm actually going to sacrifice Y. Okay, that is if I want to do that using, on that discrete. If I want to do that on that continuous, what I'm actually going to do, okay, you are giving f of x, y. You're looking for f of x. Okay, we're looking for f of x. You're actually going to integrate this, okay, over the range of y. Okay, when you integrate this, of course, you put the range of y, you're actually going to see y will be eliminated. Okay, you're only going to have a function of x. And similarly, you may also want to get f of y. Okay, if you want to get f of y, okay, minus infinity to infinity, I'm just talking about using the overall range, okay, f of x, y, okay, it's actually going to be the x. Look at that. If I'm looking for the marginal distribution of y, I'm actually going to integrate the joint density given with the, over the range of x, which means I'm actually eliminating x. And if I want to get the marginal distribution of x, then I'm actually going to integrate the joint over the range of y. Okay, that's what I'm going to do. Okay, that's what we call marginal. Okay, okay. So I'm going to go to the next slide right now. Now, going to the next slide right now. From the example that I gave you before, how can we figure out the marginal probability mass function of x? For instance, I want to do, what is the probability of s equal to 1? What is the probability that service time equal to 1? Of course, if I want to figure out the probability of service time equal to 1, then I'm going to add, over the range of y. Now, let me take you back to the table. Look at that. Service time equal to 1. I'm talking about this. You're going to sum that, okay? Service time equal to 1. You're actually going to sum this, okay? That is, we give you the probability of s equal to 1. Of course, I'm summing this over the range of y. So that's going to be 0.12 plus the 0.08 plus the 0.01. If I want to get the probability of service time equal to 4, of course, I'm going to sum across. I'm going to sum that. If I want to find the probability that service time equal to 3, I'm actually going to sum that. If I want to find the probability that service time equal to 2, I'm actually going to sum that. Okay? So you guys can see that now. And that is how to figure that out. And if I want to find the probability that the number of units, okay? If I want to do that for the number of units right now, I want to focus on y. I want to sacrifice x. And of course, I'm going to sum row wise. Now, take a look at what I'm going to do. I'm actually going to sum row wise. I'm going to clean this right now. Now, if I want to find the, let's say for instance, if I want to find the probability of y equal to 1, okay, the probability of y equal to 1, I'm actually going to sum this. You see that now? That's what I'm going to sum. That's going to give me the probability of y equal to 1, okay, because right here y equal to 1, okay. Now, I'm going to sum 0.12 to 0.08 plus 0.07 to 0.05. Okay, and if I want to find the probability of s equal for y equal to 2, okay, let's say for instance I actually want to find the probability of y equal to 2. Of course, I'm going to sum this. Look at that. If I want to find the probability of y equal to 3, then I'm actually going to sum this. Can you see that now? That's exactly what I'm going to do. Okay, that's what we mean by marginal. Okay, so that is exactly what you're going to do. Okay. And of course, that is what I'm actually talking about right here. Finding the probability of s equal to 1, finding the probability of y equal to 1. Okay. We have had an example under discrete. Okay. How do we, excuse me, how do we figure out marginal PDF? You know, for discrete, I said marginal PMF. That is a marginal probability mass function of x and y. But if I want to talk about, continuous variable, I'm actually going to do the marginal PDFs of x and y, which is the marginal probability density function of x and y. And of course, I'm actually going to be, I'm going to be giving f of x, y, which is the joint. Okay, that's going to be a function of x and y. Okay, and of course, if I'm looking for f of x, the marginal for x, of course, I'm actually going to integrate that with respect to y. When I'm looking for f of y, I'm actually going to integrate that with respect to x. I think you get it now. And let me tell you this: the under the discrete, okay, if you are trying to, the discrete problem, if they want to give you two variables that are jointly distributed, you can be given in form of a table for, for discrete. And you can also be given in terms of equation. I'm going to say that again. For discrete, you can be given in terms of a table, given a table like this, and you can also be given in terms of equation. Okay, and but for the continuous, you are not going to be given a table like this because it's not counting. Okay, but for the continuous, they're going to give you an expression. Okay, now what I want to show you right now is so I'm still going to talk about that. Now that you understand how to figure out marginal, okay, how to figure out marginal, in the case of discrete, then I want to walk you through conditional probability right now. Conditional probability distribution. When we're dealing with a probability, of course, I walk you through what we call the marginal, getting the marginal probability, getting the probability of the joint, and I also walk you through how you can find the probability of of a conditional event. Of course, the probability of A given B, for instance, is actually going to be the ratio of the joint to the marginal. I think you know that, and that is actually what is going to that is what is going to happen. I think you get it now. So and that was why, if you take a look at this, if I want to talk about in a discrete situation, okay, based on the example that we're talking about, okay, what is, we're talking about the service time, we're talking about the number of units, okay, we may want to find what is the probability that if the service time equal to this, given that the number of given a particular number of units, what is the probability of a service time given a particular number of units? In our company, where we got three different units, okay, and we got four from 1, 2, 3 up to 4 hours, okay, we can actually determine what is the probability that given a particular number of units, okay, what is probably that they're actually going to spend a particular number of hours, okay. And of course, if I want to do that, of course I need to force I need a ratio of the joint, this is the joint, to the marginal, okay. That is the conditional that we talk about, okay. So the probability of x equal to I given that y equal to j is actually going to be the ratio of the joint, okay, to the marginal. And of course, when you take a look at this joint right here, that is what we specified in the table. That's a joint. All these values here are joints, okay. This is a situation where x equal to 1, y equal to 1, situation where x equal to 2, y equal to 1, and so on like that. So the values you have in a cross-tabulated table are joints. Okay, so and then for continuous, of course, the f of x given y is actually going to be equal to the ratio of the joint to the marginal. That's what we call conditional probability. But right now, I'm actually going to walk you through how you can figure out conditional probability in a situation where two variables are discrete and they are jointly distributed. Okay, we want to go back to that example right now. The example on service time. The example on service time, and then the example on service time and the number of units. Okay, the example of on service time and the number of units. Like if you take a look at what I want to find right here, what is the probability that give the number of hours is going to number of hours spent is actually going to be 1 hour, given that the job was assigned to unit 3. Okay, so I'm going to walk you back now. Take a look at that. The service time is X, the number of units is Y. So don't forget that the aim of this company is to be able to assign, workers, to residences, and in such a way that their, allocation at the end of the day will be efficient. Okay, that's what we want to figure out. But what we want to do right here, of course, is just that what is the probability that given that the service, given that the number of units is 3, what is the probability that that unit will actually spend, okay, 1 hour? Okay, the probability that the 1 hour is spent, given that that unit is unit 3. And of course, if I want to do that, okay, x equal to 1, y equal to 3, that's going to be 1 and 3. This is not 13. Okay, this is just trying to say, x equal to 1, y equal to 3, 1 and 3, then divided by, this is going to be marginal. Okay, the marginal for what? That is, it means what I'm trying to talk about right here, this guy here, give me 1 second. This guy here is actually talking about, it's the same thing as the probability of, x, probability of x equal to 1 and y equal to 3. Okay, and this guy here is the probability of y equal to 3. Look at that. Okay, you can see that now. So look at that. Probability that x equal to 1, comma, y equal to 3, that is P13. Can you see that now? Let me write that clearly. I'm actually going to write that clearly for you to see. Okay. Excuse me. I'm going to write that clearly for you to see. Okay. So x equal to 1. Okay. So x equal to 1. So what I will talk about is that the probability, the conditional probability is actually going to be equal to the ratio of the probability of x equal to 1 given that y equal to 3 divided by the marginal, which is the probability of y equal to 3. Okay, so all what I'm trying to talk about right here is just that, okay, if I'm looking, what I'm trying to say is that this guy here is equal to the probability of x equal to 1, y equal to 3 divided by the probability of y equal to 3. That's exactly what we're going to use. Okay, now we need to first figure out this one. What is the probability that when x equal to 1, y equal to 3? We're going to go back to the table. Now, when x equal to 1, y equal to 3, look at that, x equal to 1, y equal to 3, that would be 0.01. You can see now? That's actually going to be 0.01. Okay, so that means the joint is going to be 0.01, and that was the reason why we actually have 0.01 right here. Okay, and what is the probability of the marginal? The probability of y equal to 3. Okay, of course, the probability of y equal to 3, of course, is actually going to be that. How do I got that? How do I got probability of y equal to 3? You're going to go back. Y equal to 3, you're going to sum all that. You see that now? You're going to sum the row. Those are what I showed you before. And that was how we got that. Then you're going to do the ratio of that. And this is the probability. That is the conditional probability we're actually looking for. Okay, so if that is taken, I'm actually going to go to the next one right now. Okay, so the next thing that I actually want to talk about, you remember in probability, I walk you through what we call independent events. We can also talk about independent event right here. Okay, if you have two variables, like two variables that are jointly distributed, whether the two of them are discrete or whether two of them are continuous, of course, we can actually find a way to investigate whether the two of them are independent or not. Okay, and the only condition for them to be independent, of course, we're actually going to follow multiplication rule. Okay, so for them to be independent, of course, the joint, in discrete case, the joint probability must be equal to, when you multiply the marginals, okay? And the same thing will be continuous. When I have f of xy, okay, and then if f of xy can be written as a product of the marginals, then we're going to conclude that x and y are independent. Okay, so, and that was why I said, how is this independency different from the independence among events? Okay, is the same. Okay, only that this time around we're using probability function. Okay, we're using probability function, but in the case of the probability that we did before, we're using probability associated with events. Okay, so I think I put another example right here. You can actually work on that on the discrete. Okay, you can work on that. Now, the next thing that I actually want to talk about now, I'm still on discrete. The other time I told you, if they want to give you two variables that are jointly distributed, of course, if they are discrete, they're going to give you in terms of a table, okay? They're going to give you like a table like this, okay? And just like the one I showed you before on the service time and the number of units. And you know what? You can also be given in terms of a function. Look at that. If you are not going to be given in terms of a table, you can be given in terms of this. And you know what? Do you know that from this, you can actually formulate a table? And what if I ask you to formulate a table, okay, from this? What is the range of x? Of course, the range of x is 1, 2, 3. What is the range of y? The range of y is 1, 2. You see that now? Do you know you can actually formulate a table? This is a function of x and y given. You can use this f of x and y to actually generate a table. And of course, if you want to generate a table, okay, the table you were given before, it's actually going to be in this form. I'm going to show you now. You're going to have it in this form. Like, if you want to do, let me see, that is a 3 by 2. If I have something like that, okay, and I have x comma y, okay, x is going to be 1, 2, 3, and y is going to be 1 and 2. You see that now? Because I have the range of x is 1, 2, 3. You can see that now. And the range of y is 1 and 2. Okay? And how can I find this? 1 and 1 means when x equal to 1, y equal to 1. Okay? I'm actually going to come here and make use of this. And that is going to be 1 plus 1 divided by 21. And that will be 2 over 21. It means this guy here is going to be 2 over 21. Then I can also find for 1 and 2. Look at that. This means when x equal to 1 and y equal to 2. Of course, when I plug in the value of x equal to 1, y equal to 2, when I plug in the value right here, of course, you're actually going to have 3 over 21. Okay, x equal to 1. And when I plug in x equal to 1, x equal to 3, and y equal to 1, like I said, of course, you're actually going to have 4 divided by 21. And when I plug in x equal to 1, y equal to 2, of course, you can fill up the other one. So all what I'm trying to tell you right here, of course, you can actually construct a table based on the equation given. Like I said, the first one that I did, this is the values of x, and these are the value of y, okay? 1, 2, 3 for x, 1, 2 for y, okay? When x equal to 1 and y equal to 1, that's going to be 1 plus 1. That would be 2 over 21. Okay, when x equal to 2 and y equal to 1, you're actually that's going to be 3 over 21. Okay, when x equal to 3, okay, and y equal to 1, that was going to be 4 over 21. Then you can also fill up other ones. Okay, but you know what? How are you going to know whether you are right? If you add all the probability together, it must give you 1. Okay, watch out for a question like this where you're going to be given a function of x and y, and they are going to ask you to construct the table. Okay, so now, do you know that from this question they can ask you different kind of question, figure out the marginal, figure out the independent, figure out conditional, and so on like that? Okay, now consider the equation. If you really don't forget that it's discrete, right? X and Y are discrete, random variable, and they are jointly jointly distributed. Okay. Now, if I ask you to find f of x, which is going to be the marginal for x, what are you going to do? You're actually going to sum, okay, over the range of y. Okay, now take a look at that. If I want to get f of x right here, getting f of x, I'm actually going to be plugging in the value of y. Okay, if I want to get f of x, okay, that's going to be x plus 1 divided by 21, then plus x plus 2 divided by 21. And that was why we got something like this. Look at that. So what I'm trying to talk about right now, this guy here, okay, which is a marginal. Did you get that now? That is a marginal. So that is the marginal distribution of x. That's what we call the marginal distribution of x. You see that now? So what I just said that you're going to sum that if you're looking for the marginal distribution of x, you're actually going to sum, the variable, you're going to sum that, the joint, with respect to y, okay? And don't forget the y goes from 1 to 2. Look at that. Y is from 1 to 2 as specified, okay? Similarly, you can do the same. If you want to get the f of y, the marginal for y, you're actually going to sum that over the range of x. And oh, give me 1 second. Oh, give me 1 second. That should be network. Okay, I think it's back. I'm actually gonna. Okay, so let me see. Is it back now? Okay, it's back right now. So sorry for that. Okay, so like I said, if you want to find the marginal for y, okay, finding the marginal for y, you're actually going to sum the joints over the range of x. And what is the range of x? The range of x from 1 to 3. Take a look at that. I'm actually look at that. The x is from 1 to 3. If I'm looking for the marginal for y, I'm actually going to sum the joints over the range of x. And that's exactly what I'm trying to do right here. What am I doing? I'm actually plugging the value of x. 1, this is for 1, 2, 3, and I take it 1, 2, 3 because the possible range of y is 3. Okay, so then you have this. Okay, so what I'm trying to talk about right now, um this guy here, this guy here is a marginal for x, and this guy here is a marginal for y. Okay, and you know what? Do you know you can investigate? If I ask you to investigate whether X and Y are independent, what are you going to do? Oh, what you're going to do, you're going to investigate whether the joints can be written as a product of the marginals. Look at that. Okay, so that's exactly what you're going to do. Okay, that's what you're going to do. Okay, so which means if you multiply this guy by this guy, okay, does it give the same result as this guy here? Okay, if I multiply f of x by f of y, does it give exactly the same result as this? If you give that, then that is the only condition for you to conclude that x and y are independent. Otherwise, x and y are not independent. If x and y are not independent, that means they depend on each other. Okay, they depend on each other. Okay, so that is exactly what I'm talking about. Now you know how to figure out the marginal from a given joint discrete probability mass function. Okay, so I'm actually going to erase that right now, and I'm actually going to go to the next slide. I'm going to go into the next slide. Okay, so going to the next slide. Oh my God, that is incidentally the last slide. Okay, so I want to appreciate whoever that is going to be watching the video. And once again, I want to apologize, for the mix-up, that happened during the lecture time. Okay, and that was the reason why I decided to make a new video. For those of you who may need clarification, okay, of course, you need to meet with me during my office hour. My office hour is going to be 10 to 12 on Tuesday. 10 to 12 on Tuesday, That is you know, the central time, the central US time, which is Chicago time. Okay, but for those of you that are outside, outside the central time, of course, you got to know that the time is central time. 10 a.m. to 12 noon on Tuesday. Okay, okay. So until on Wednesday, that I'm actually going to come your way again. Make sure you stay safe and protected, and have a good night. Bye for now.